worry. Yeah, just put in the pocket. So I should start. Recording asset. Okay. So I should hold this or something. Okay, so I think everybody and I think every. Mm-hmm. Yeah. So is the sound clear? So I think everybody understood this is a small seminar on special relativity. I will give a brief introduction, discuss some problems. That's what I'm aiming to. So yeah. So how many of you are like comfortable with special relativity? I mean, at least know up to the stage of like Lorentz transformations, energies. Huh? Not? Okay. Yeah, it's fine. Like I just asked it. Okay, so I'll start the talk. Just anyway, though, I'll come to that after giving the introduction. So yeah, so first I'm gonna say why we needed such a theory, such a new theory, while we had Newtonian theory and stuff. And then I'm gonna do the sum of the derivations so that we can. I'm not going in deep, but to the level that we can do the problems and we can understand what is happening. And to the stage, if some of you want to study like special relativity or general relativity later, so that you can understand book. So that what my aim is. My aim is not to teach you special relativity, but give you an introduction. And I will discuss some problems, including the twin paradox. Okay, so before Einstein, in the 17th century, we had Galileo, Newton, who formulated the laws of physics. So if you ask me what's in my opinion, the most influential papers ever submitted is one, Principia Mathematica. Anyone disagree? The second is on the electrodynamics of moving body, where Einstein published the special theory of relativity paper. I don't want to say the Germany thing. I tried to spell it, but I couldn't correctly. So what is the relativity before Einstein is called Galilean relativity. Of course, Galileo came with it. So what is Galilean relativity? Suppose there's a car going, a person inside the car take a gun and shoot the bullet at someone. He shoot the bullet at a velocity, v, with respect to him. And we, physicists, are standing here and we are looking at it. We don't care if the guy die or something. We only need to measure the velocity of bullet with respect to us. We only care about that. So when we measure that, according to Galilean relativity, we will get it is u plus v. Yeah, everybody knows that. Now, we are considering the same thing. Now we are going a little more peacefully. Instead of shooting the person, we are just flashing a light at it. So, with respect to him, the speed of light is c. So the flash will go in speed c. But what will be the speed of the light when you look from the ground? According to Galilean relativity, it should be u plus c, right? Agreed? Because it was u plus v, there is nothing special, so it should be u plus c. Okay, that was there for the 17th century. And after that, maybe within a century, then we got the electrodynamics, started by people like Benjamin Franklin, Coulomb, to Maxwell, Faraday. And Maxwell, he's in the late 19th century. He formulated like every equation, every electrodynamics laws that he had, he formulated in a single group of equations, we usually say 4 equations. And according to that, and he found light is electromagnetic wave. You first study light is a particle, then you study light is a wave, then you again study change, then you come to light is an electromagnetic wave. You come to that by Maxwell. I think after some time we will say light doesn't exist, but I believe light exists. So, but when you solve the Maxwell equations are supposed to be invariant in every inertial frame. Everybody know what an inertial frame is. Okay, inertial frame is where there is no acceleration, it's constant velocity. And Maxwell equations should be true in all inertial reference frames. But when you solve the Maxwell equations, you will get a solution of a wave. You get a wave solution. You can call it like, it's called D'Alembert solution, D'Alembert's operator and stuff like that. So from there, you will get that speed of light is constant. So at this time, I remember, I forgot to add that. There is, do you know about Leonard Susskind? He's one of the founding fathers of string theory. Have anyone been? So he's a nice guy to like get an introduction to physics. Like, not a, like, he's a great physicist, but like his class are not like that advanced. He don't go like, he take class in like open course kind of thing. Yeah, so in his book, there is this thing, there is this derivation, and then Maxwell says, let there be light. So that's how light is formed, because you get the equation, a wave solution, there is C in it. And the light, which is electromagnetic wave, can only have the velocity C with respect to all inertial frame. But that's never a problem, because me physicist who was standing ground looking at the car, so the light was speed to be U plus C, right? According to Galilean relativity. So there's some problems with these two. These are not consistent. These are not consistent equations. So what happened was, now we are coming to late again after Maxwell formulated, there was this idea of ether. So ether was kind of jelly-like liquid, fluid that is spread all over the universe, which is a absolute frame of reference, which is said to be absolute frame of reference, and we are going past there. And the hypothesis was that Maxwell's laws were correct only in that absolute frame. So that is a special frame. But I think there is, have anybody heard about Michelson-Morley experiment? So Michelson-Morley experiment, what it does it is trying to find if there is a medium like that and Earth is rotating through it, then we will detect it, because the speed of light will be different in the direction we are going. Yeah. So we should detect a change in speed of light. But didn't. The speed of light were constant in all direction as observed. And now after that, there were even physicists many people tried to, say it is true by this, but everything breaks out. And then Einstein comes, our Grandpa Einstein, or Uncle Einstein, whatever. He came, and both Newton and Maxwell were his kind of, let's say, role models. But he understood both of them cannot coexist. He should either one of them are wrong or both are wrong. So Einstein worked on that, and on this year 1905, called the miracle year, where he published 4 papers. Not just 4 papers, 4 evolutionary papers, one on photoelectric effect, one on Brownian motion, and 2 on relativity. So he published this. So on his paper on the electrodynamics of moving body, of course in German, he introduced the special theory of relativity. It was called the theory of relativity then, but after 10 years, he introduced the general theory of relativity, which accounts for gravitation. So we call it special theory of relativity. I mean, yeah. So he had 2 postulates. So first of all, what is postulates? In math, we will say axioms, but in physics, it is not okay to say it axioms, because it is not that obvious to be an axiom. We are experientially observing it, so it is our experience that is saying it's a postulate. Even quantum mechanics is also built on postulates like this, Bohr's postulate and things. And okay, so in special relativity, there are 2 postulates. One is laws of physics apply in all inertial reference systems. By this, we basically mean laws of physics, majorly the electrodynamics law of the Maxwell equations. They should work equally in all inertial frame of reference. and speed of light in vacuum is the same for all inertial observers. So this should be true. The speed of light should be constant for all inertial observers. Now, this is where we build our theory. Not our theory, it's Einstein theory, but yeah. And one more thing I have to say is that in every physical theory, there is two more things that kind of like more like axiom. That is, one is homogeneity, which says that there is no preferred position in the universe. And next is isotropy. The words are correct, right? Yeah. So that is there is no preferred directions. So isotropy says there is no preferred direction, and homogeneity says there is no preferred position. So from that, let's try to do a problem. So I have a light clock. This is what is called light clock. So it is basically I have in here. I have it's not mirror, like I just copy paste a Google. So it's a particle, a light emitter and detector. So a light emit, the clock start ticking, and the light goes there, reflected, and it will detect. We will look at the time. We'll stop the ticking. So we measure time with this. Okay, so I have this thing. So I take it. I press the button. It goes up. It goes down. I see it is taking t0 time to do it. Now, you guys are still, so now for you guys also it's t0, right? There's no difference. But now I start running, okay? I'm taking this and running like this. So, now you will see the light to travel in diagonal. But now you look at the geometry. So, I will take this. So, this will stay to be d. There is no difference in that. But now, when you look at this distance is changed. There is a distance here. So we can, like, from the first equation, we will get t0 to be 2d by c. And now when we do apply Pythagoras theorem into it, we get Vt by 2 is this length. And that square plus d square is equal to Ct. Ct means this distance, light travel distance, Ct by 2 square. So now when you solve it, you will get this equation. So there is something wrong because Newton says time is absolute. We all feel time is absolute, right? I was born, when was I born? 2006. And someone was born in 2005. And that guy will be 1 year older than me. It's not changing. So we don't observe time to be observed, but it is. So this is called time dilation. So Professor Date has mentioned this. Now we need a transformation that would count for this. So what is usually the transformation you use? Let's say in y direction and z direction there is no motion. I am assuming that in the whole seminar. I will be working on only t and x, y and z to be constant. So usually a thing is x is equal to x minus Vt. So this is the normal. So x dash is equal to x minus Vt is a normal transformation we know in Newtonian mechanics. But that changes now because this won't count for the things that we observed later. So these are the new transformations. So this is what we found. Okay, the gamma is called the Lorentz factor. Is the 1 by root of 1 minus v square by c square we got there. And now t dash into gamma into t. This we didn't got later because we assumed x could be 0. We are taking at a nearest point. We didn't assume anything else. And this should be x dash is equal to x minus Vt according to Newton's law. But there's a gamma in this. So in the whole seminar you will see a gamma coming to every physics you know. Yeah, so I recommend writing this down because you might need it later in the seminar because these are like important things. If you're not comfortable with this, please write it down. Huh? This. Here. Huh? No, this t minus vx by c square. What are you saying with the same? No, dimension equal doesn't mean they cancel out. I don't get what you mean. Like, it's not, dimension analysis doesn't work here. Here v is velocity, c square is a constant. X is not the velocity, v is not the velocity of x. X is our reference frame. Look at the reference frame. In the reference frame, the x, y, z is fixed, and x dash, y dash, z dash is going parallel to the y axis with respect to us, with velocity v. So these are called the Lorentz transformation. So why are these called the Lorentz transformation? Einstein didn't found this. This was Henrik Lorentz who found this first time, but he used that only for, like, he used it in such a way that you should do this transformation when you do electrodynamic problems. He introduced it kind of like that. He didn't had any like why it is correct or just electrodynamics are true under this transformation. He just stated that it's not like it was universal or it applied to every mechanics. Nothing like that was there. So yeah, did you noted these? Yeah, like the y dash and z dash noted just these two equations. Yeah. So now we are going back to our problem of the shooting thing. So okay, now if you differentiate this, you will get the new velocity addition to be this equation. So this is v of a with respect to c is equal to v of a with respect to b plus v of b with respect to c by 1 plus vab vbc by c square. So this term that is below was in Galilean relativity. So that was the problem. Now let's go back to the problem we discussed where the flash is lighted. Now we substitute VAB is equal to C, VBC is equal to U as in that problem. We'll get speed of light with respect to ground to be C. So our postulate, which was speed of light in vacuum is the same for all inertial observers, is not violated. And yeah, so if it was violated, then obviously the postulates are wrong. But this means whatever you put, if you put C, U is equal to C, you will get C. Whatever you put, you will get the C there. That means speed of light is constant for every inertial observers. So are you convinced that this will be always less than C? Okay, I will write it down. So where is this? Oh no. Sorry for that. Yeah. So VU by C square. So are you convinced that this is always the norm of this is always less than or equal to C? This is the function we usually see, x plus y by 1 plus xy. So this should, that is less than 1, so this will be less than or equal to C. So are you convinced this is true? So this implies nothing can travel faster than speed of light. So this is the speed of light C is the universal limit of speed. So you cannot pass that. My friend Flash claims to pass that, but I don't believe it. Okay. Now, yeah, so this page, it's not very necessary to understand special relativity in the introduction level, but I like to think about it in these terms. And Date showed this equation, right? The space-time interval. Yeah, okay, in his notation, these pluses over minus and minus over pluses, that's just a notation. Like when you are looking for a book in relativity, especially general relativity, first look at the front pages, you will see what notation it is using. It's just for their convenience. I am happy with this, so I use this. And this value, this ds square is equal to minus c square dt square plus dx square plus dy square plus dz square is an invariant under Lorentz transformation. What does I mean by that? So if I calculate this measure, this ds square in one frame, let's say in the rest frame, and another person who is running, and if we calculate the same value it will be same. Like whatever inertial reference frame you're calculating, this is a constant. So ds square is a property between two events. By events, what I mean is a point in space-time, that is, it is associated with one time dimension, then x, y, z. That is what I mean by space-time. So a point in space-time means, event means a point in space-time. So for between any, let's say there is an event A and there is an event B, this ds square between them is not the straight line length or something, but yeah, this will be a constant. This is the property of the two events. And from this you can see that this is kind of look like the Python distance, right? Pythagoras distance. But now you can say a dimension, new dimension, ICT, is there in new to our calculations. So yeah. And proper time in my notation, it is defined as d tau square is equal to minus ds square. If this minus will not be there in maybe another notation. And by proper time, what I mean, let's say there is two events happening at a single position. Okay, I have this, I throw this at one point, I catch this. Now I measure the time in my watch. That measurement is the proper time, that is also the space-time interval between these two events, me throwing it, me catching it. Now, when you go past, this time will not be the same for you. Instead, because my space is changing. Okay. So, yeah. No, it is true for multiple directions. It's true as vectors too. Like, no, this will be vectors. This will be vector. This will be vector. This will be dot product. Wait, was it dot product or product of norm? No. This VABBC. This will be the dot product. No, right? The product of the norm, like. Right? Yeah. Huh? Yeah. Okay. So like in special relativity, you can it's better to work with one dimension because almost everything you can just take the new x direction to be through the word line. Yeah. So the concept of proper time is very important because we will be using that when I am explaining other problems. And proper velocity, you don't have to like think why it is, but we will like proper velocity. We add proper in the sense that they are easy to transform in Lorentz transformations. So proper in the sense that this is something I shouldn't go to 4 vectors. This is a relativity kind of thing, but when I say velocity, I will mean our normal velocity. When I say proper velocity, I will say proper velocity or relativity velocity. So don't confuse that. Yeah. Now I am going to the momentum and energy part. So we all know momentum to be mv for a mass and v velocity. Here it is gamma mv, like how gamma came everywhere. Here also gamma comes. And so how this comes, it's not a guess solution or something, but you can, like, momentum is something conserved in a collision, right? So it is easy to, it's not easy, it's computationally a little, like, it takes some time, but you can literally derive this by considering a collision between two particles. You will see this value will be the conserved quantity and not the old momentum. So this relativistic momentum will be conserved, obviously, if there are no external forces. And from now, momentum, I only means relativistic momentum. I don't consider the classical momentum anymore. So I only consider the relativistic momentum. And now we want to reach the whole equation, right? So do you understand the integral? So this is integral f dx. You know, energy is equal to integral f dx. So this is that f is dp by dt. And now to this, it will become v dp. Then you apply product rule, you will get to be gamma mc square. So of course I should write it. Okay, this is, I think, will be the most famous equation in the world, maybe. So people don't consider the gamma. People can say it's a notation, but So also, in here, the electrostatic energy is also considered like electrostatic momentum. And yeah, in the absence of external forces. And this is considered in every case. It's not like, usually we say kinetic energy is considered in a collision of elastic collision. Here there is nothing like that, because usually the energy is lost as like heat, sound and stuff. But when you come to relativity, this equation counts for all of them. There is a say that hotter bodies are heavier than lighter bodies. So all of these tend to change the mass. That's how you consider this. And now when you square this thing and subtract p square c square, you'll get m square c to the power 4. This is, I would say, the most important equation in special relativity, because whatever you're dealing with, collision or whatever, this is the value you will be using very frequently. And this is an invariant. Note, energy is not an invariant, because energy explicitly has V in it. This is not an invariant. The energy of a thing I see when I was running is different from when I was staying down. But the energy is this value, the E square minus P square C square, which is equal to M square C to the power 4. That is a Lorentz invariant. That means whoever look, they will calculate this value to be same like the ds square. So this has another meaning, of course, but like the ds square, the same thing, but like for another vector thing. And I will try to introduce if I get the time about that, but I'm not sure about it. And now we'll see. We know these things will come like 1905, but physics worked before that. There were some problems, but we used it for many things. We used to calculate projectiles, we used to for vehicles, we used them. So if our theory says Newton is wrong, but it doesn't agree with the observation, it is wrong. But we can see the kinetic energy, which is E minus mc square, if we do the Taylor expansion of this, you will get it to be half mv square plus higher order term. So why is this not here? Because it's very small. I will show how small it is in the next slide. This half mv square, it is a Newtonian kinetic energy. So it's a very good approximation, because this is a very small value. Now I want to say something. This is relativity unit. People work in relativity with this unit because, one, they don't want to work with C square to the power 4 everywhere. You don't care about that anymore. Also, when you work in relativity, when you put C in there, every values are like super small or super large. You don't get normal values that you comfortable working with. But when you put C, you will get normal values. When you do relativity calculations, you will get good values. So we put C is equal to 1. There is no unit. There is no meter per second. Just C is equal to 1. So that means time is now calculated in meter. I mean, we calculate space in terms of time, right? We say light year, same conversion, reciprocal conversion. We say time is calculated in meters. Okay, so I will be avoiding these in many cases, because, for example, the twin paradox image, it will not look very good if I didn't put this. So I don't have to like put CT here, I can just put T here. And it is very like, by direct dimension analysis, you can directly convert after you get a result. Yeah, so V will be less than or equal to, the modulus of V will be less than or equal to 1 now, because the maximum is C, which is 1. So V will be always less than or equal to 1. Okay. Huh? Not light. If you put V is equal to C. Okay, I think I should say that. Okay, from here you can see that. Okay, I will explicitly write the equation. Okay, now when you look at this equation, if we put V is equal to C, you get this to be 0. And if M is not 0, this is infinity. Okay, but there is no sense in saying infinite energy, right? So that is why if M is not 0, then V cannot be C. We will be strictly less than C, as I said. But when you put M is equal to 0, this is 0 by 0 form. So it doesn't mean, it can mean something. So that means speed of something is C if and only if the mass is 0. So usually the particles are light and gluons. Gluons and the you know those for the nuclear interactions. Yeah. So that's another reason why we cannot accelerate it something of definite mass to C, because as you go, the energy required will be going to infinity. So it is impossible. So now this is what I said. I will how the order of change. Like Newton was correct. Like up to very good approximation, he was correct. How correct he was? The maximum speed ever a human reached is 11,094 meters per second. That was when the Apollo 10 returned from the moon and re-entering the Earth. Earth's gravity pulling it, and it reached a very high velocity. That's a maximum a human has traveled. But for them, what was V by C? It is 0.000037. And when you consider gamma, how many zeros are there? 9, I guess. Yeah. 1.9 zeros, then 6, 8. So Newton's laws will be correct to a very good approximation because the gamma is very small. Now, what is the fastest man-made object? I'm not talking about electron and proton we creating in the detectors. The fastest man-made object is the Parker Solar Probe. It reaches speed of, what is this? Yeah, 1,76,000 meters per second. And for that, this is not that small, but still, V by C is 0.00058. This is very recent. We know relativity. Without knowing relativity, we cannot do this because our calculation will be wrong. It will not be reaching sun. It will be reaching somewhere else. And the gamma is even smaller. Like then you take the square and under root and stuff. So Newton laws are good for our daily purpose. Like okay, the technologies we have are using it, but Newton was still correct up to a very good approximation. That's why like most things will, like when you considering a vehicle, I don't think you will do realistic approximation on it. Yeah, so with this I think you will get a good introduction. I hope you have got a good introduction to special relativity. And now we are gonna do some problems. Problems in the sense, I have 4 problems and 4 of them are intended to in 4 different things. Like you might not have noticed. It is bringing something new, some new things that you might not have noticed in it. The first is magnetism. So everybody knows current carrying conductor creates magnetic field. So we know this is the Lorentz force. Okay, this is the Lorentz force. This is the force experienced by a point charge in an electric field E and a magnetic field B. Okay, so here there is a current going, but there is no net charge in it. So there is no electric field in it because the current is a current carrying conductor with the current going. It is electrically neutral. And the particle is going right with a velocity u. Well, let's say we can, velocity u. Now what will we see? When you look in the lab frame, when we are looking from here, there is current, therefore it create magnetic field. There is no electric field, so the particle get a force upwards, I guess. So the particle get a force upwards due to magnetic field. Okay. Now my question is, what if we go to a frame that is going to the right in a velocity u, as same as the charge q? We are going to the right in a velocity u, where in that reference frame, what will you see? No magnetic field, correct. It's not about not magnetic field, you cannot say no magnetic field. No magnetic force because velocity is 0. But the velocity is 0. There is no force due to velocity. No, force is something we observe. We have to observe force. Because when we are looking from the lap frame, it is going upwards. It has a force upwards. So it will go like this. But when you are in this frame, when you are moving with it, there is no magnetic field. But this should go up. We are in an inertial frame. It should be true, right? It should go up. How? No, there is nothing called expanding. There's only Lorentz contraction. No, you're almost correct, but there's no expansion. There's only contraction. That's enough, right? Yeah. No, that's a very good guess. The same thing. Yeah. Yeah, exactly. So this is one of the major achievement of relativity because he could explain the theory of electromagnetism, how electric field and magnetic field works. Yeah. So this is what happens. Okay, let's say I'm assuming the V in here to be equal to U for simplicity. So when we are in this frame, this charge is at rest. These positive charges are not moving. I mean, it's moving this, but for simplicity, let's assume it is 0. But the negative charge are moving even faster. Okay, we can get that by our velocity addition rule. It is not 2v, it is something new, but we will get by 2v by 1 plus 4v by c square. No, not 4v, what is it? V square by c square. And that means it is going very fast. So it is it is contracted. So the density, can I use the word density? I don't know. So it is dense. I would say it's dense. The negative charge is more dense. So there is more negative charge when we look from this point of view, and there is no current. And therefore that means there is a net negative charge in the current carrying conductor, which will create an electric field. So we have a force. And the electric field is negative, so the electric field should be upwards. So it's correct. And I haven't included the math, but after the seminar, I can show the math if you want. And it will give the same result as the Biot-Savart's law. The electric field, the force will be exactly equal. Charges are invariant almost everything, yeah. No, I didn't say that. I didn't say that. Yeah, charges are invariant. Yeah, okay. Then when Q is moving, there is no force on it because the magnetic force need a velocity. So it is just staying there. Yeah. Yeah. Charge is not being created. No, it's a something you see on it. It's a like this is flowing charge. You cannot. It's not like you can define a boundary. No, the charge is still conserved. Okay, okay. So, okay, my point is these equations create up the result we observed, the Lorentz transformation and Lorentz time. They're only true when we are perpendicular to it. Far away it changes, and I will introduce. That's my last problem. Yeah. So now I wanted to introduce something that I will use to So, did you understood the magnetism thing? Yeah. So, yeah, I was really baffled when I saw this. Like, I was really, what do you say? I don't know the word. Yeah. Hmm? I wanted to introduce. Yeah. So, I wanted to introduce a concept called space-time diagrams, which is just time and space. I'm not considering other. I should. So, in here, first of all, I need the concept of word line. By word line, that's the locus of points in the space-time. Like if, let's say I stand here without moving, my word line will be like this. I'm just going through time and not going through space. Okay? At the same time, if I somehow am not going in time, this is impossible, but then I will be like this. So it will be somewhere between, right? Okay. My last statement was wrong. Sorry. So first of all, let's consider what will be the slope of a line in this. It will be t by this will be 1 by v, right? The slope of a line passing through the center. So if you put c, which is 1, we'll get a line of 45 degree. So to get this to be 45 degree, I put c is equal to 1. So this is a word line of a light passing in the positive direction. This is also a word line of light. So a word line of light will always make 45 degree with the x-axis. Now our velocity is less than 1. That means the slope is greater than 1. So our velocity, our word line will be here. Only in this area. We cannot, the word line of an object cannot go before that. And light will always have that word line. And from this, we will say everything inside these. Inside these, you can say, when you consider in 3D, it is cone, called a light cone. So everything inside this area, this is called the time-like. This time-like separated. Every point in this is time-like separated to origin. You can also observe that for the time-like, the ds square be less than 0. Let me make sure like the other convention make greater than equal to. So time-like, yeah, time-like it's less than 0. You can just think like this, because time-like, when time increases, this becomes 0. I mean less than, this decreases. Time-like means delta s square is less than or equal to 0. Less than is 0. Equal to strictly less than 0. That means this area. This is represented by this area. It's a equation of cone. X square minus t square. And if it is greater than 0, we say it is space-like. So this is space-like. This is time-like. So if it is inside the cone, it is called time-like. And if it is outside, it is called space-like. You can to check something is time-like or space-like, just look at this. So this is, let me. Okay. Now if it is 1, what has, not 1, sorry, 0. What has delta s square is equal to 0? Yeah. So it is called light-like. So if something is if the angle between something is 45 degree, like it's on a line with slope 45 degree, it's called light-like separated or null separated, you say. So what does it mean? It means that, let's say, one event A happens at origin. So the light cone, the time-like area of the event A is this area, right? And this is space-like. So let's say there is an event B happening here. So A and B is time-like separated. As A and B is time-like separated, B will always happens after A. Or A will always happen before B. By always, what I mean is whatever reference frame you're looking at. Okay, if I see I'm at rest, I see this as B, I observe that B is happening after A, you run. You will also observe B is happening after A. But the notion of simultaneity breaks if they are not time-like. If they are here, let's say C. Now A and C is space-like separated. That means C is not in the light cone of A. That means C is not in the, okay, this light cone part is called future of A. This is future and this is past. So C is not in the future or past of A. So what happens is, let's say for some person, it may happen, one may happen first, the other may happen next. For other person, it will be the opposite. So you cannot, there is no meaning of simultaneity when something is space-like separated. Something is space-like separated also means they will happen at different, they cannot happen at the same space. They cannot happen the same space. Okay? Because if they are happening at the same space, then a person standing there exactly know which happened first. And exact like time-like cannot happen the same time point. Okay. Yeah, so I hope you got a basic idea about this, lot more to study in this. You're welcome to study on this. I can suggest book after this if you want. So I introduced this because I'm going to solve the twin paradox by this. So what is the twin paradox? Let's suppose Flash has a twin, and when they were 10 years old, I will call this Flash younger Flash, this Flash older Flash, even though they are of the same age at 10 years. The younger Flash goes away from home. He just ran away, continued in straight line for 7 years. He calculated 7 years. Now that's the thing. When you work in relativity, you have to say who did the thing, who did the thing. It matters who did the thing. So now the young Flash calculated the time. He started running. He has a clock in it. He saw, oh, it has been 7 years. Now to go back. Okay, then he go back. But the other Flash is staying at home. He's very decent. But when young Flash, who I'm calling the young Flash, come back to Earth, he literally became the young Flash. I just named him young Flash. Now he literally became the young Flash. If they started at 10 years, now young Flash has only 24 years. He ran for 7 years, he ran back for 7 years. But he is 60 years old. He's retired. I don't know, he may be dead. Who can say? So what happened? So there's nothing paradoxical in it, but if someone thinks there is something paradoxical, the thing is, when you think like this, when they both start, the older Flash sees the young Flash, time to go slow. That's what time dilation is. If someone is going past you in a velocity, we'll say their time going slow. If Flash look at him, their time is going slow. That means when the first older look, the younger time goes slow. When the younger look, the older's time will go slow. So you might think they are equivalent, right? Then why should someone be older than the other? Because inertia frames are equivalent. The answer is obvious from the image. That's why I included this image. There is this point. He's not an inertial observer. He came here, he took a turn back, he did an acceleration to go back. So he was in a non-inertial frame for some time. So that is what caused the aging. You guys have seen the movie Interstellar. The same thing happens due to the gravitation, this general relativity, but still, due to gravitation, I really don't remember. Oh no, I don't remember the name. What's his name? Huh? Yeah, not Murph. Murph is older when he come back. Yeah, so because he spent time near the black hole, he older a lot. So it's kind of like that, but that's a different thing. There's time dilation due to general relativity. This is time dilation due to special relativity. So what happened is when he did the acceleration, his notion of time entirely changed. The notion of time entirely changed within a minute time he accelerated. So yeah, from here you can see this was his word line. At this point, he changed his word line to a new word line, which is symmetric to the y-axis if you consider like t-axis if you consider like this. So that's what is different from him. So to get these values, you calculate the proper time. That's why I introduced the proper time. You can calculate the proper time in this and proper time in this. The proper time in here will be the 50 years. Proper time here will be 14 years. So that's a change. This is real value for v is equal to 0.96 c. So I think there is nothing paradoxical in it. Everyone is clear. Any doubt? You can ask any doubt if something is not clear. I'm flat earther. He can literally run. Okay. So I'm going to the next problem. So this is one of my most favorite problem in special relativity. So the thing is, a lightweight pole, you know, the athletic thing, it is 20 meter long. Okay? There is a lightweight pole 20 meter long that was on ground near a barn which is 15 meter long. So I should draw this. Okay. So then what do is flash picks up the pole, go far, and he runs with it. He runs with the pole, as in the image, towards the barn. This is the barn. Okay. This is an open. There is a door here, and Batman is. Should I draw Batman now? I shouldn't. This is Batman. Batman is staying here. The flash is coming from here with the pole. So he comes here. So I need you guys to calculate some things because just to try something. I'm not telling you to calculate everything, but one thing you have to calculate is when Batman looks at the pole when he passes like here. I told you these things are only true when it is perpendicular. So when he is here, what is the length of the pole? Yeah, 12 meter. I think that's correct. So when flash looks, what's the length of the barn? When flash looks, what is the length of the barn? Barn was originally 20. Now he is running. You remember the muon thing. So muon sees as small. Sees the distance as small. The same thing happens here. 9. Yeah. Okay. Now, do you know why Batman did this? Flash caused some problems to Batman. He just wanted to lock him inside his high security barn. So as soon as he entered, Batman just closed the door and locked it. Okay. Now what happens? Yeah, so the length of the road, let's consider it in the, okay, do you agree that Batman can close it? Because Batman see the length as 12 meter and the barn as 20 meter. So according to him, a 12 meter can go inside. And he saw this and he closed the door. It is now sealed. Okay, he put a password that he even don't know, let's say. But when Flash looks, he have a 20 meter port. He's going to put it in 9 meter. That's half the length. He couldn't take the half of it inside. What happens? He sees it is inside and he's locked it. Huh? No. When? No, he comes from, he's far away. Then he take the barn. He just run. Here, he run with a constant velocity from here. Huh? Yeah. Yeah, why? But for Batman, he's sure he saw it and he closed it. Flash. Frame of reference of Flash. No. He cannot put it inside. How can you put a 20 meter pole inside a 9 meter barn? Have anybody seen this problem before? This is a very underrated problem in physics. Huh. The ladder, I mean, this is called in many other names. So. Huh? The stick frame is same as flash frame. Yeah. My question is, do anyone have an answer to this? Huh. We need assumptions, not results. If you have seen this, don't say this. No, special relativity is true in every inertial frame. That because it has that because another reason, not this. That because the energy it has and stuff, right? Let me just drink some water. You're kind of near, but your reasoning is wrong. Yeah, your result is true, but the reasoning is wrong. The thing, this is, you cannot do this as answer. Kind of the road breaks, you can say. So, I'm going to the answer. So, anybody want to do a last guess? Why? He has a answer, but why? Huh? No. Nothing has to do with energy. I mean, yeah, no, not in the way you think it is. Okay, I will go to the answer. The answer is that I'm assuming, not assuming, these things are, let's say they are made up of particles, this rod. So how is this a stick? Why is it not falling apart? This has an equal and opposite force. Okay? This force actually travels at the speed of sound. And even if it travels at the speed of light, there is a time, there is a distance for it to cover. So when the first particle goes, which he holds, the other particle will not be following it. So, when you want to state the conclusion, there are no rigid bodies in special relativity. This is one of the most important results because I didn't know the result and I tried doing some problems and I got some weird result, but then I realized there is something like this which resists us to create rigid bodies in special relativity. So this is a very important thing. There are no rigid bodies in relativity. Yeah. Huh? It was a different problem. I got it. Yeah. There is no like really rigid bodies. Huh? Which? No, there is no point in when there is no rigid body. He can't even run with this. It breaks. If you go, if it is going in the speed of sound, which is way smaller than, like, for example, the example I show, the Apollo was going at 36 Mach or something, 36 times the speed of light, a speed of sound. That is very small compared to C. The C still V by C was 0. There was 40 something. Yeah, yeah. So you shouldn't be considering like rigid bodies without considering like we should be very careful when you consider these things. So what's the conclusion? Moral of the story is, if you run fast, you may die. You will die. Okay, so I'm going to my last problem, which is a very non-trivial problem. I don't think anyone would have heard about it. Okay, so the problem is, I'll come here so you can get the same idea. I have this cube. It is always white up and green to this side. Okay, so this side has red, this side has orange. Now, this has same orientation. It is fixed in this axis. Now you are staying there. This comes very fast. It's a 0.8 C to you. What are the colors that you will see before it passing? Somewhere like, huh? You don't consider Doppler effect. I'm not talking about Doppler effect. Assume if the color comes, you will see the same. What will you see? Which part? 0.8 C. I just said speed. Don't consider Doppler effect. Don't consider Doppler effect. Doppler effect, you will see these things like red, right? Blue, whatever. Red, yeah. Yeah, so this is coming like this. So which parts can you see? Green, red. Okay? Everybody agree that if I run from here to this, you will see green and red. Everybody agree? Before it passing, me passing you. Not sure. It was just because I was going slow. So I think this will be the most unusual way, unusual thing you would have heard today, maybe. You will see the orange. You may see the orange. You won't see the orange for the whole time, but for maybe a grade, or depends upon many things, you may see the orange which is in here. Light, let's say light emit from this, orange light emit from this, consider same thing. It is very unusual. It's, yeah. Once I say the reason, it may be obvious, but. And this is not a like famous problem or something. This is like very specific thing. Very few people discuss these things. Huh? Hmm? Can you say that? Huh? It will be somewhere like, I mean, it depends upon very value. You won't see it that way. You will see it in this value, this side. Okay, that's an image of this. So here, the dark lines, this is a cube. You are standing at the bottom. You are standing here, AB, in the level of AB. So, the dark lines are the things that you will see. So here, dark line with this face you will see. Well, this is my, how much more time can I take? How much more time can I take? Yeah, because this is not a like. Yeah, that's it. This is my last problem. I will be ending it with this. I can't understand. Like if you have this, this is the green. This is orange. You are seeing the orange. The orange is in dark. Yeah, this part is in dark. It is back. This is the orange. You are seeing green. You will see green. There is nothing wrong with that. You will see green, but instead of seeing red, which is in this thing, which is dotted, you will be seeing orange. His explanation was almost correct. Yeah, I think it was correct. I couldn't like formulate it correctly. Like. A, B, F is green. A, B, F dash, B dash is red. A dash, E dash, E is orange. So you have seen orange and green. You are sitting like this. You are sitting like this. Okay? And this pass like this. No, red will, like, when you see, red is visible, right? I can see the red. No, it's because when it is very fast. I will be seeing that part, which is very unintentional. How will I see this part? Yeah. No, in this case also, you'll be seeing red, but not for a definite interval. Not always orange, but for some time interval, it will be orange. Like the maths is too messy, like geometry stuff. Huh? Red? Yeah. But there will be some time you will be seeing orange. It depends upon many things, the distance, velocity, length of this and everything. This has nothing to do with Lorentz contraction. This has nothing to do with Lorentz transformation. Yeah, it does. You can see the image. Look, you're also seeing it curved. This is because of Lorentz. This is also not because of Lorentz contraction. You will see it contracted or big. You will see it big really for some time. Huh? No, it is not about kinematic. It's about something else. Yeah, the distance between these are causing it. If it's a point particle, it doesn't happen. Because it has dimension, it is happening. If it has a point particle, it will be happening as the induction. I mean, also like all properties are not there. So, no. I mean, the dimensions are the reasons which is happening. Yeah, say. Okay, so should I say the answer? Huh? There is. I don't think it will be seen for small velocity, but I don't know which. It depends on many factors. You can try the math after, like, I explain why it is. It's like the math is messy because of trigonometry. Huh. No, there's nothing special in it. That is a property of that speed depends upon the dimensions, the distance. Okay, will depend on two things: the dimensions and the distance between the perpendicular distance with the line. It depends on two things. Okay, so I will say the answer. The answer is causality. So by causality, I means nothing can travel faster than light. So light travels at finite speed. You have never considered that light travels at finite speed. In this case, the speed of light is very huge compared to this. But when this is, I think this is an image of for 0.80 or something. And maybe more than that, not less than, of course. And this is what you will see when it make 30° with you. Just giving the details. I'm not sure. I can refer it if I want. It's something above 0.8, of course. Not above speed of light. You can't go above speed of light. I'm saying nothing can go speed of light. And speed goes in speed of light. Light goes in speed of light. So what happens is, like, okay, now I will try to explain this. I will explain this in another frame. Now I am going to the frame of, you people are still staying at this frame, but I am going I'm sitting on the above the cube. Okay? So I'm not considering the curving, okay, here, like just above. I'm sitting here. I only have head. I'm sitting here. So at some time when this is recorded, you are here. Okay. Now, this emits a light in this direction, right? Okay, from anywhere, from let's say here. It emits a light. I'm calling this light orange. Oh, that's too. I'm standing. So the orange light has begun from here when you were here. But you are going very fast. And now when I'm in my frame, you are going here with the velocity v. Right? By the time this reaches here, you will always be here. You'll be already be here. Because this is the explanation. Huh? This is in the cube's frame. So the reason is, within the time it comes here, you are already there. But you will be still seeing it coming from that angle. I have to mention this. Angle make very weird sense in relativity. They are also not invariant. Huh? Yeah, you will be seeing it coming from there. Even though in this distance it doesn't make sense. Yeah, we'll be going this way. Yeah, yeah. No, that is no. When it emitted this, we were here. It is when it takes time to travel this distance. For the light to go from here to here, it will take time. Distance by c. By that time, we will be here. But it emitted to us. We saw it from that side. This is very hard. I have like 2 weeks on this to do the math. So yeah, before and maybe even after, you could say. I don't remember. I tried to plot this on Mathematica, but Mathematica refused to do it for some reason. Huh? The speed of light is constant. It is finite. Okay, so what I mean by that is, there is one, when you say something is non-relativistic, you mean is speed of light is constant. You can see that if you put speed of light to be infinity, these are just Newtonian. This time is equal to time, this goes to 0, everything is as Newtonian. So by relativistic limits, non-relativistic limit, we take the limit c tends to infinity. And there is something else called c goes to 0. Superlativistic, hyperlativistic, some name like that. That's very weird because there is no dynamics in that case. I don't know much about it, but there is something like that too. We treat it in theoretical physics. So this is the thing. So, right, the speed of light is constant. It's finite. That's a point here. That is called causality. Nothing can travel faster than speed of light. So in the first problem, I came into the electromagnetic equivalence. Second, I went to the what happens when you change reference frame. Third, rigid bodies doesn't exist. Fourth, speed of light is finite, create weird vision to us. Our vision should change when you study special relativity. Once you practice this, this will be like you will get trained to these things. That's the point in physics. The point of studying physics, get very accustomed, whatever that word is, to. So with this, there's an important application for this. For example, if I was a teacher and I am doing a quiz for you, I have the answers in mind. I shouldn't run very fast with the answer sheet because you will see the answers. That's why process work very slowly like this. If I run like this, you got the answers. There's no point in me doing the quiz. Huh? Yeah. So, yeah, I think the time is over. I wanted to, but I didn't create any slides for it. So. Okay. Light clock experiment. Huh? There is no perpendicular velocity. We are. The only velocity is in light path. Here. Huh. Then also the time dilation will be there. Now there will be length contraction too. It is best to come here, then derive the Lorentz contraction, then go back to it. Let me see if I want to say something else. So do you guys have any doubts? Are you guys staying here? Are any of you guys staying here? Okay. If anyone is staying here and want to discuss more about this, you would like to study general relativity, I could introduce 4 vectors. There is something called 4 vectors. Then when I teach it, many things will be obvious for you. So I could discuss it with you if anyone want to. Because when you go to, it's always, I always recommend to deal with those things than these variables, these quantities. So I think I have covered everything. Yeah. So thank you. Thank you for everyone. So anyone have any more questions? I mean, I'm not assuring I can answer every question. I'm not like an expert in it or anything, but I can try.